For this video, I'll be introducing you to the tree data structure by implementing a generic unordered tree, where all nodes contain same information and can do the same type of operations. The goal is to get you accustomed to some common tree terminology and algorithms before we dive even deeper into the tree world. Let's get started. I'll be using a single tree class for this, so I'll go ahead and create it, and jump into a few private properties like children. For this, the children will be a map, but you could also use a linked list. So as a matter of fact, check the linked list videos and I challenge you to change this implementation after to use a linked list instead. But I'll be using linked lists in some other trees later on as we go. Add parent as well, and next I'll create an ID which I'll randomly generate using math random and date. This is what will make any node unique and allow us to have nodes of same name under the same parent. And speaking of name, I'll add that as well, which I set in the constructor, but I'll first make sure the name is specified and is a non-empty string, otherwise throw an error. Then I'll set some getters, first for the name, and make sure when the name is being updated, the same check is performed as well. I'll add an identifier getter to return the ID, another for the children, which will simply return an array created from the children map values iterator, another for the parent, and I'll call it parent node, and finally one to return the children count using this map size. So let's try this by instantiating the tree with the root as name, and proceed to log from name to the children information, and as you can see, everything is as we expect, an empty tree with no children and parent. So let's add some methods to take care of those. The first method I'll add is to be able to create a child node. And all it does is takes a name and create a new tree and add it to the children map, then return it. Remember that any node in a tree is essentially a subtree, since it may contain its own children as well. So let's try this and call it with a name for our child node. And if we check our logs, it now says we have one child node. If we log this new node, it may not be obvious, but the parent of this node is now null. So I'll set a parent setter, which only updates the parent if the new parent is different than the current and only takes null or tree node as valid parent nodes. Now if we check, we can see that the new node now has a parent. I would like to see the whole tree structure as a string, so let's create a method to print the whole tree. And all it does is console log the name of the tree concatenated with the result of a recursive method call, because one of the best ways to traverse a tree is with the recursive functions. So I'll call this method getTreeString, which will be private. It will take a node and a space count to indent each node to represent the tree nesting. Inside, I'll create a variable to hold the string, which will contain a new line, so each node is printed on a new line. Then I'll loop the node children and concat the space repeated space count times plus node name plus call to the getTreeString with the child node and a space count plus 2, and 2 here is the indentation. What will happen is as it goes deeper, the space will increase by 2. Then in the end, I'll just return the string. So let's try this now. As you can see, the tree is now represented as string and much easier to follow as we continue with this implementation. I can continue to create more nodes, but I'll first get parent, then create nodes, and create child nodes as well by alternating between the create call and parent getter. And I can go as deep as I want easily, and this is pretty much tree traversing and creating nodes at the same time. Next, let's add a method to check if the node contains another node. It can take a name, an identifier, or a node, and I'll call it needle. And first thing I check is if the needle is a node by checking if it is instance of a tree, then return the result of a call has on children. Otherwise, I'll loop children list and compare it against name and identifier and return true if matches, and at the end, I'll return false. Now that I look at this, I don't like this ID random generation since there is still a chance I may get 2 nodes with the same ID. So let me create an ID generator and I'll call it unique ID, and it will be a self-invoked function that returns a closure, which inside contains a generator function, which the start value is the date now in milliseconds, and I'll just yield the start value plus 1 infinitely. Then I set the generator and return a function that returns generated next value. Now if I replace the ID here, I should be fine. And as you can see in the logs here, the ID is now used the unique ID generator. Let's also add a method to get child node that takes the name or the ID. And we'll just loop the children, check the argument against the name and identifier, and return it. Otherwise, return null in the end. Now I can check if the tree has the first node, as well as getting the to node, for example. All seems to do exactly what we want them to. And so far, these are super simple methods. And as we go, you will realize how all these methods are actually super simple implementation. Now, let's add another method that takes either a node name, or ID, and I'll call the argument needle as well. First, I make sure this is a child node with has child node check. Then I check if it is a tree and use it as identifier to remove it. Also loop the children and check it against the name and identifier and delete it. We also need to set its parent to null, just in case there is a variable holding reference to this node, to make sure it does not lead back to this parent before it got removed. Now if I remove the first node here, we will see that the tree no longer print the node, and the reference we have of its node was updated with parent null. This remove method only removes direct children, and this sets the rule that only a parent can remove its children. Now, what if I want to add it back to the tree? Let's add a method that takes a node and adds it to the tree. I'll call the method append child node, and it will set the new node in the children map, as well as reset its parent to the current node. Now we have two problems, and the first one is related to the parent. With current implementation, I can simply get a node and update its parent, and its previous parent will still contain it as a child node. One way to fix this is to make the parent node just a getter, but I want to take the setter challenge to show you some stuff. So what we probably want for this case then is to, whenever resetting a child parent node, we remove it from its current parent node child nodes by calling remove child nodes. Also, if I go ahead and assign the parent node to node 2, we notice that the 2 printed on the side does not contain the pre-node. But pre-node parent is the 2 node. So whenever that happens, we want to call append child node on the new parent inside the parent node setter. But we want to do that after we set the parent property to avoid max call stack error. If we check now, we will see that the 2 node now includes the pre-node, and the pre-node parent is the 2 node. All this by taking advantage of methods we have already created. The other problem is that I can now append tree inside pre-node, knowing that tree is the parent of pre-node, and we get a call stack error. This is because we create a circle relationship where parent contains child and child contains parent. Also, I can go ahead and append pre-node inside itself, and this will completely remove it from the tree. So we want to handle these two cases in a much better way. So the first thing we can do is to make sure the node we are inserting is not the same as the node taking it. Otherwise, just throw an error saying the node cannot contain itself. And we see this error now instead when we try to append pre-node on itself. Else, we grab the current parent, and while parent is not null, meaning while parent node is not the root node, we will check if it is the same as the node being inserted and throw an error if that's the case. Otherwise, update the parent. If I try to append tree inside a pre-node, I'll get a descriptive error now. This should even take care of case where if I remove pre-node from tree, then append tree on pre-node and try to append pre-node back on tree. I can also check if no node is passed, or if it's not a tree node, or if the node is already a child node, and quit early as well, to avoid this loop altogether. As you can see, the parent-child relationship can get complicated, but the solutions are still easy to implement. This is all because we are dealing with the instance here. If this was just objects like JSON and JavaScript object, it would be easy to introduce repetition and circular dependencies. But with instances, it makes checking them much easier. Again, there is probably 1,000 ways to implement this, from easy to complex depending on what you want to accomplish. But the tree fundamentals will always be the same. Now, the last thing about trees I haven't shown you is the traversing part, which is the desire to visit all nodes if I want. I already shown you traversing with the print method to print a tree as a string, but I haven't got much in detail on that one. With this tree implementation, traversing is probably the easiest part, So I'll just create a traverse method that takes a callback, and we loop over the children and then call the callback with the node, and right after call traverse on the child, passing the callback. What this will do is depth first traversing, which means it will visit a node, deepest node, before moving to a sibling node. So if we try this and simply log the node name as we traverse, I'm expecting to see 1, 1, 1, 1 deeper, then 1, 3, then 2, and finally 1, 1 again. We could also provide a way to quit early by checking the callback return value. If it is true, then return true for both calls. Now we can break if a node matches a name we were searching for, just by returning true. We can create so many other methods now using traverse method, like removing multiple nodes at once, collecting multiple nodes, etc. For example, let's use this method to create a find by name method that takes a name and use it to search. So I first set a found node to null and traverse the tree with a callback where I check if name is the same and set found node and return true to break out. Then I just return the found node. If we search for any node, it should be easy to find any node now, but this will return only the first match. So let's create another that returns all the matches since we have 2 nodes in the tree called 1, 1. You can use that to test with. For this one, we don't want to quit, so we search all nodes, checking names, then pushing the match node into the children array, then return it. If we search for the 1, 1 node, we should get an array with both. Use this tree to explore some ideas or simply play with it. I left the link to this code in the description. I would like to turn it up a notch and show you a file system tree with a user interface so you have a feel of what you could use a tree structure for. Leave questions in the comment section below. Please like, share, and subscribe for more content like this. Thanks for watching. Catch you in the next one. Bye-bye.